Data Representation Lesson 5 Sound. Contents: recap on binary addition, recap on characters, recap on images, and the new content for this presentation, how computers store sound. Binary recap. Just a quick reminder of how computers represent data. All data inside a computer must be represented in binary, using a combination of zeros and ones. In this example here that we've seen lots of times before, we've got the denary number 13 represented as the binary value 1101. This equates to 13 since we have a 1 in the 8 column, a 1 in the 4 column, and a 1 in the 1 column. So the 8 plus 4 plus 1 equals 13. To recap on binary addition, we have this example that we've seen before where we're going to add together the binary for 4 and 9. So the binary for 4 is 0100 and the binary for 9 is 1001. To add these two binary numbers together, write both one above the other. Make sure that you line the columns up because it makes the maths easier. And then start by working from right to left. So 0 plus 1 is 1. 0 plus 0 is 0, 1 plus 0 is 1, and 0 plus 1 is 1. In binary arithmetic, your answers can only ever be a 0 or a 1. There is no 2. So in this example here, where we've got 1 plus 1 in binary, 1 plus 1 in binary cannot equal 2 since we don't have the symbol for 2 in binary. And there's still quite a few students who are writing down 2 whenever you see 1 plus 1 in binary. What you have to do in binary when you get 1 plus 1 is instead of writing 2 down, it becomes 0, carry 1 into the next column. So always double check. If you're adding binary numbers together, a 1 plus a 1 never equals 2. It is 0, carry 1 into the next column. Okay, we've also looked at how computers store characters. And as with everything we've looked at, we'll identify that whenever the computer needs to store something, whether it be a character, whether it be an image, or a sound, it has to first convert it into a number. So what we have to do to get characters into binary is first of all assign each character a unique number. In this case, the capital letter A has been assigned the number 65, and this is the ASCII standard code for the capital A letter. ASCII will give us a total of 256 different codes. However, as we previously discussed, we also need codes for special characters with accents, different languages have different alphabets, and also we need characters for things like emojis. Quite quickly, in ASCII, we'll run out of these 256 different codes. So an alternative method to coding letters to ASCII is called Unicode. And Unicode gives us just in excess of 65,000 character codes. The complete list of all characters that a computer can represent is what's called its character set. Since this is the final lesson on data representation, it would make sense to pause the thought at this particular stage before we look at how sound is stored. Can you, for instance, explain how the binary number system works and can convert numbers from binary to denary and from denary to binary? Can you add two binary numbers together, including binary numbers that have carries? And can you explain what an overflow is, when you add two binary numbers together and the result becomes too big to store? Can you also explain how characters and how images are stored? If not, go back, review these topics before you continue with this presentation. The basics of how computers store sound is very simple, and it goes back to this whole idea that anything the computer stores has to ultimately be represented as a number and then converted into binary. So sound occurs as a wave, as we can see in this diagram here, and the sound needs to be sampled at regular intervals, and each sample then needs to be converted into a binary number. We will see how this happens on the next slide. So, this graph on the right-hand side of this slide represents a sound wave. And what we need to do to get this sound wave into the computer is sample it at regular intervals. And each of these red dots represents a sample taken of the actual sound wave. Time across the graph goes across the bottom, and amplitude goes up the side of the graph here. So at each sample point we need to measure the amplitude of that sound. So at sample time 1, for instance, the sample is the amplitude value 3.2. At sample point 2 in this sound wave, the second red dot, the sample amplitude is 3.9. At sample point 3, it's 5, and so on. Once we've sampled the sound at regular intervals and we've measured the amplitude, we can then convert this amplitude into a binary number, thus representing the sound in binary format. So to recap, how does the computer store sound? The sound is sampled at regular intervals, the amplitude of each sound sample is measured, and then this value can be converted into a binary number. Just to pause here to do some deeper thinking, how accurate is the sound that's being represented if we are sampling it? We'll discuss this on the next slide. One of the important points to recognise when we are storing sound digitally inside of a computer is that we never actually store an accurate representation of the original sound. Because we're sampling the sound, we're not storing the details representing each individual unique quality of the sound that we're recording. We're only recording a sample, a small subset of the original sound. So here you could see, for instance, in figure 1, we've got an original sound wave. This sound wave has been sampled in figure 2, and the resulting digital representation of this sound is shown in figure 3. And as you can see, the representation of the sound in figure 3 looks significantly different to that in figure 2. Therefore, the quality of this sound would be poorer. What we can do, though, is to get better quality, we can up the sample rate. So for figure 4, we've doubled the sample rate. We're taking twice as many samples. And as you can see in figure 5, the resulting sound wave that we have stored digitally is much closer to the original, although still it's not 100% accurate. So there are two main factors that affect the quality of the sound that you're storing digitally: sample rate, and then what we call sample size or bit depth. Now, sample rate is simply how many samples that you take per second. In other words, how many times do you chop the sound up into individual parts each second of sound. And the more samples that you take per second, the better the quality of the sound, as we saw in the previous slide. The CD quality sound has its sample rate set at about 44,000 samples per second. So for every second of CD audio that you are listening to, there will have been stored 44,000 samples per second of that audio. Now, of course, the more samples that we take of the audio, the higher the quality of the sound, but also the more storage space it will take, since we need to store more samples. The other factor that affects the quality of the sound is the sample size or the bit depth. Now, this is determined by how many bits are used to represent each of those individual samples. CD quality sound uses a sample size or a bit depth of 16 bits per sample. And again, the higher the bit depth, the better the quality of the sound. But of course, because you're storing more bits per sample, the file size of the sound file will be larger if the bit depth or the sample size is larger. So let's pause for thought again. Do you understand that sound occurs as a wave? Can you explain how this wave is turned into digital data by sampling the sound wave at regular intervals? Can you explain the effect of the sample rate and the bit depth on the quality and the size of the original sound file? If not, go back to the previous slides, have a look at them, come back and see if you can answer these questions. So that's the end of the data representation topic. Hopefully now you should be comfortable at converting numbers between binary and denary, carrying out binary addition, explaining how characters are stored, explaining how images are stored, both bitmap and vector-based images, and explaining how sound is stored inside the computer. If you're still not completely certain about these topics, then the best bit of advice I can give you is to go back to the previous quizzes and the previous videos. Make some notes. Try and set yourself some questions. Try and answer those questions. Maybe even explore YouTube and have a look for some videos that might explain it in a way in which you can understand more clearly than how I've done in these videos. But what's really important is that you don't give up trying to understand these topics. Some people understand these topics more quickly than others, but ultimately, given time, everybody should be able to understand the topics that we've looked at under the heading of data representation.